Now I'm going to take all that we have learned and put it together and see how we can apply this to a real world circuit. What is it that is given to us in the real world, and how do we apply these concepts that we have learned in this module to solve those real world problems. Okay, so let me consider a very simple example first. Okay, so first we will do what is known as static timing analysis. Timing analysis is something that you do on a circuit given that the sizing has been done already, which means that the delay of that gate is fixed. Okay, we'll solve the sizing problem next. So let us assume that we have done the sizing and I will indicate the delay inside the gate. An inverter has 1 unit delay. The NAND has 2 units delay. Okay. The NOR I'm saying has 3 units of delay. Let's say you have sized it like that and therefore the delay is in that fashion. Okay. So the terminology is, this is your black box circuit that you have. These are my primary inputs, PI1, PI2. This is primary output 1, primary output 2. Okay. We define something known as an arrival time. Arrival time is basically the time at which the output of that gate will be stable. The minimum time after which the output of that gate will be stable. Okay, so you could have some transitions and then it will stabilize to that output. Okay, that's what we are calling arrival time. It is min time after which output of the gate okay. So if I have a logic gate with say n inputs, okay, if I ask you when will the output of this gate be stable, the minimum time after which it will be stable, well, obviously it depends on when the inputs arrived and when the inputs were stable, right? If the input switches after some time, of course the output will also change. So the output arrival time is indeed related to the input arrival time. Okay, and in general, if I have delay from one input to the output all different, right? So if I have input I, 1, 2, n, and my output is just one of them, then let dij equal to delay from ith input to output, right? I can remove the j. Typically in whatever I've shown here, this 2 is the same for both inputs. It doesn't matter which input to output we are looking at, the delay is only 2. In most cases, this di is similar. Okay, but the arrival time at the output of this gate, therefore, will be what? Maximum of arrival time at the ith input plus the delay from the ith input to the output. Correct? So this is arrival time at the ith input plus di. Okay? This I will say a small ao. Clearly there is a maximum operation that we have to perform here. right? By definition, arrival time at primary inputs is 0. They arrive at time 0, right? It's just a definition. So arrival time here, okay, I'm going to mark it in red, is 0. What's the arrival time at the output of the first inverter? Let me label them. I1, I2, NAND gate N1, I3, I4, N2 and I5. What's the arrival time at the output of I1? 0 plus the delay through the inverter. Therefore, you get arrival time of 1. What about arrival time at I2? It will be 2. What about arrival time at N1? Be careful here. It depends on when the other guy came. Depends on when the other guy comes. So therefore, you got to first solve for I4. What's the arrival time at the output of I4? 1. Now therefore, the arrival time at this node is also 1. Now you have to do max of arrival time at first input, which is 2 plus 2 and 1 plus 2, and therefore this will be 4. What's the arrival time at the output of I3? 5. Okay. Now, so therefore the arrival time here is 2. What is the arrival time at the output of N2? Yeah, you have to do 2 plus 3, 1 plus 3 and take max. So you get 5. What's the arrival time at the primary output? PO2. At PO2. 6. Okay. So now I can define what is known as a critical path. The critical path is the path from input to output which results in maximum time for the input to, for any input to propagate to the output. That means after the critical path time, every output will be stable. Okay. So what is, now how do I calculate how do I find the critical path? I take the maximum arrival time and then back propagate, right? So to calculate the critical path, I don't know, I'll take 6. Then I come one step back. It is 5. Now for the NOR gate, which side should I go? Should I go towards I4 or I2? I2. Again take the max there. Go back. This guy. Then I go back here and go here. Therefore, the critical path is like this. Right? So that is called the, this is called the critical path. Okay. So now I'm going to flip the problem. I gave you the sizes, I gave you the delays, we could find a critical path, we could do some analysis. Suppose I didn't do that, right? I had to now do my gate sizing problem on this circuit. What is the gate sizing problem on this circuit? I need to find the input capacitance of every gate so that the latest arrival time at any of the outputs does not exceed a timing spec. This is what I need to do, right? So I'm going to flip this now. Then PI1, PI2, PO1, PO2. You are now given a timing spec. Which means that the maximum arrival time, right? Meaning is max AT. Okay, I'm going to call this arrival time. AT at any primary output should be less than or equal to T spec. Right? Only then I can guarantee that the circuit will function at this particular speed. There is no input combination that can cause the output to be stable after this T spec. That's what we have done here. Okay, remember. So what is this? This analysis, by the way, that we did earlier is called static timing analysis. Here, what are we doing? We are considering all possible combination of input variations and ensuring that the output in the worst case does not exceed some particular time. So here, for example, it might be possible that a particular path that we have marked here may not even be realizable in hardware. In the sense, not realizable, that pathway may never get activated because of certain input combinations. But still we are considering the worst case delay there. You get it? So if I have an NAND gate with the input always tied to 0, the output will be 1. The input switching on the other thing is not going to affect the output. Right? Therefore, if I say that, the output is of that NAND gate is going to depend on the input to which is always connected to 0, it doesn't make sense. But we are still considering those as well. Worst case timing analysis is what we are doing in static timing analysis. This is called STA. Okay. So now, using the previous example and whatever we have learnt in this course, what is it that you would do in order to do this sizing problem? So what did we learn? We have learned how to optimize the path delay of a given path. The delay of a path we know how to do. Now clearly, because there are maximum number of gates in this path, we might say, okay, let us pick that path and optimize the delay of that path. Right? It's a fair thing to do, because that's going to give you the largest delay. And if you ensure that the largest delay is less than T spec, then you are fine. But unfortunately, you saw in the previous example that the other output arrival time was not far behind. It was only 5. Right? So let us see what happens if I apply this path delay sizing problem to this circuit. What will I do? I will now start sizing this particular path, right? I1, I2. Let me just make sure my notation is correct, because I can switch from slides to this at some point, right? So that okay, yeah. Let me not call this I1, I2. I'm going to call this 1, 2, 3, 4, 5, 6, and 7. Okay. The output, of course, there is a load capacitor that has to drive some load capacitance. So what will I do? I will now pick this inverter, this NOR gate, this inverter, and do my path delay sizing. In the process, what are you going to do? You will end up upsizing the gate progressively. From input to output, the gate sizes will start going up, or the capacitance start going up by what factor? Stage effort. It goes up by the factor of the stage effort, right? Therefore, this will be increasing size. In the process, what you will do is you will increase the capacitance on this node. Now, if you increase the capacitance on this node, you are going to increase the capacitance on this node as well, right? On node 2, capacitance on node 2 will go up, which means now that this path delay may go up. Likewise, this path delay may also go up. Because that NAND gate, right? Wherever the no, not that path delay actually. This cannot go up. It is only the other path delay that can go up, right? Whichever is connected to that inverter I1, I2. Since the NOR is connected to I2, that delay can go up. Similarly, this delay can go up, right? In effect, what we have done is we have in order to optimize the delay of one particular path, we have ended up increasing the delay of the other path. And there is no guarantee that in this process of gate sizing, what we identified as a critical path initially will remain a critical path always. It can easily switch at any point. Effectively saying, you cannot do path delay based sizing on an actual circuit. Simply because I have exponential number of paths. Exponential in what? In the number of nodes. So if I have n gates or n nodes in a circuit, then this is O of, exponential of n, the number of paths. And there's no way I can optimize all the paths simultaneously because I cannot even enumerate all the paths. Forget about sizing all the paths, right? So first thing is path sizing, not scalable. Okay? In the interest of time, I will just switch to these slides, right? So that you just get a quick feel. I want to complete this today. So what I'm going to do now is I'm going to show you how people moved away from a path-based formulation to a node-based formulation. That means if you have n nodes, the number of equations and other things should be O of n. Then it is solvable. Of course, if you have a large circuit, it will take a long time to solve. But it should be still in the order of number of nodes of the circuit, right? So this we did. Arrival time at the kth output is basically max of arrival time of the input, and all that stuff, right? So let us assume that the output, the capacitance on node 1 is xk, right? So let me just copy this. Okay. So what we are saying is the capacitance on the gate whose output node is k, the capacitance of the input is xk. This is going to be x6, this capacitance. Similarly, this capacitance here will be what? X3. Okay. So this is basically going to be x1, is it? Oh no, that cannot be the case. X3 is x3. Oh no, sorry. No. This one is x3. This is x2, x2. x5, x5, right? And this is basically x6. This is x4, x7, x1. Okay? These are my variables. My variables are, as usual, are my capacitance x1, x2, all the way to x7. I have to solve for this. Okay. So what is the delay of inverter I1? It is GH plus P. What is H? Yeah? X1. right? Assuming that the first inverter is a 1x inverter. Okay, let's keep that as an assumption. So H1 is basically just x1, and therefore the delay of the inverter is x1 plus 1, right? G is 1. What about H2? It is now the net capacitance on node 2 is x2 plus x5, right? Because the same node inverter is driving the NAND and the NOR. So it is x2 plus x5 by x1. That's H. And therefore the delay is x2 plus x5 by x1 plus 1. Similarly for the NAND 3, it is simply x3 by x2. Remember, it is not x3 by x2 plus x5. It is only the input capacitance of that particular thing, right? So it is x3 by x2, and the delay is logical effort 4 by 3 into x3 by x2 plus 2. Similarly, I can write down the delay for all the other gates, right? Just that, for example, in H5, in D5, you have to be careful that this inverter is driving the NAND and the NOR again. So therefore, again, it is x2 plus x5 by 1 plus 1. That's the delay. Clear? This is nothing new to us. Whatever we learned earlier is just what we have applied here. Only thing is, now I have to take this and alter my optimization. Okay. So what is now the arrival time at various nodes? What is A1? Arrival time. Remember, the arrival time at the input is 0. Primary inputs. So what's the arrival time at node 1? Yeah? X1 plus 1. Right? A1. What is A2? It is A1 plus D2. Right? What is A3? Now you should be careful. Max of A2 plus D3, comma A5 plus D3. Okay, this I can remove D3 common. D3 plus max of A2 comma A5. Okay. A4 I can write similarly in a similar way, right? Which is basically arrival time at A3 plus D4. Right? I can now write down all these things. So effectively, I have A7 eventually will be what? Arrival time at A6 plus D6. Right? What is the constraint that I have on my circuit? Given a timing spec, max of A4 comma A7 should be less than or equal to T spec. Right? This is what I have to now set up, how I have to set up the optimization problem. Okay. Now, typically, you don't try to minimize the delay of a circuit because you are given a timing spec. If you try to minimize the delay, you will make this circuit much faster than the spec, but end up burning more power or more area. So therefore, what I'm going to do is, I'm going to set up my optimization problem to be the following. I will minimize summation xk. What is summation xk? If I minimize summation xk, what am I minimizing? Area or power. Equivalently, it's power, right? It's though they are not exactly the same, you will minimize both in the process, such that max of A4 comma A7 is less than or equal to T spec. Now the maximum operation is very painful to do in optimization. So therefore I have to make this a separate, some other kind of a condition. So if I just simply break this as A4 should be less than or equal to T spec and A7 should be less than or equal to T spec. Then I can guarantee that the max of this is less than T spec, right? The other problem is the equality condition in optimization is a big problem. Therefore, what you do is you simply convert all of these to less than or equal to terms. It's effectively the same thing. These are called auxiliary variables in optimization. You just insert these variables, make all equality conditions with less than or equal to, and solve the problem. You'll get the same answer, right? Now, what's the catch here? We have done everything. Will it come out very well? You get a solution of x1 to x7. How are you sure that this is a minimum or this is a global minimum? You will get one answer. You use an optimization tool, you put these constraints in, you minimize summation x1 to xk, you will get one answer. How are you sure that this is a really an optimal? That means, is there some other sizing, some other set of sizes which will give me lesser area for the same T spec? It turns out, no. This is a convex optimization problem, and this class of problems is called a geometric programming problem. Okay? So this kind of an optimization where you have x by x1 by x2 kind of terms, it turns out it's a convex problem. Implies solution is a global minimum, right? That's a question you asked me long back, saying in path delay, how are you sure that it's path delay? Is also the same thing. It's a geometric programming problem and the solution is guaranteed to be an optimal problem. Now, what is the big thing that we have done here? What we have done is just look at the number of constraints that we have introduced. It is just O of n. If I have n nodes in my circuit, how many nodes do I have here? 7 nodes. The number of constraints are basically 7, and for each input of the gate I may have something. This is O of n constraints. Thereby, even if you give me a circuit with 1,000,000 gates, I can solve it first in reasonable time because the number of constraints is only O of n. 2, I can guarantee that that's a global optimum. There is no other solution which will give you a better delay or a better area for that given delay. Right? So this is how you take what we did in this module for toy examples of path delay and apply it to actual circuits. Your EDA tools which do timing optimization, right? You do synthesis, you get the logic circuit. Then you have to make sure that the logic satisfies timing. How does it do it? It does it exactly like this.